Welcome to this lecture on the binomial theorem. In this lecture, we're also going to review some combinatorial proofs. So let's start with the definition. A binomial expression is the sum of two terms, each of which is a constant times a variable. In the context of the binomial theorem, the term n choose r, that is CNR, or remember the number of subsets of size r whose elements are chosen from a set of size n, while this quantity is called a binomial coefficient. So here is the binomial theorem. Let x and y be variables, and let n be a non-negative integer. Then we're going to consider the binomial expression x plus y. We're going to raise it to the power n, and the binomial theorem gives us a closed form formula for this x plus y power n. And here it is. It's the sum for j equals 0 to n of n choose j times x power n minus j times y power j. So let's look at some simple examples of applications of this theorem. First, let's take n equals 0. Well, x plus y power 0, like anything power 0, is 1. So let's see if that works out with the theorem. Well, if n equals 0, then there's only one term in that sum for j equals 0. n choose 0 is 1, so that disappears in the product. N equals 0, j equals 0, so 0 minus 0 is 0, x power 0 is 1, so that disappears as well, and j is 0, so y power j is 1. So all the terms in a single product here are 1, and we do get the same answer. So a little bit more interesting now, let's look at x plus y power 1. So we can have two terms in this sum, 0 and 1. So for j equals 0, we're going to have 1 choose 0, that's 1, times x power 1 minus 0 is 1, so we're going to have an x times y power 0, or 1. So the first term is going to be an x, and then for j is equal to 1, we have 1 choose 1, that's 1, times x power 1 minus 1, that's x power 0, or 1, and then we are left with y power 1, which is y. So again, the binomial theorem gives us the right answer for n equals 1. Now let's consider the case where n is equal to 2. So in this case, j is going to go from 0 all the way up to 2. So there will be 3 terms in the sum. For j is equal to 0, n choose 0 is 1, x power 2 minus 0 is x squared, times y power 0 is 1, so we got the first term is x squared. Then we have j is equal to 1, so 2 choose 1 is 2, times x power 2 minus 1 is 1, so x power 1 is x. So we're going to have a 2, an x, and then we're going to have y power 1, which is y. So we get 2xy, as expected. And finally, for j is equal to 2, we get 2 choose 2 is 1, x power 2 minus 2 is 1, and y power j is y squared. So we are left with a y squared. And again, of course, the binomial theorem gives us the correct expansion for x plus y squared. As a last example, let's use the binomial theorem to compute the third power of the binomial x plus y. J is going to range from 0 to 3. When j equals 0, the binomial coefficient here is 1. X is going to be raised to the power 3 minus 0, or 3. And y is going to be raised to the power 0. So it's going to disappear. We're going to be left with x cubed. Then for j equal to 1, 3 choose 1 is 3, x power 3 minus 1 is x squared, so we have 3 times x squared times y power 1, or y. For j equals to 2, we have 3 choose 2 is again 3 times x power 3 minus 2, or 1, so we have 3x times y power 2, or y squared. And the last term is for j equal to 3. 3 choose 3 is 1. X power 3 minus 3 is also 1, so we are left with y power 3. And again, the binomial theorem gives us the correct expansion of x plus y power n. Now, of course, these 4 examples do not constitute a proof of the theorem. But in a later video, we're going to provide an intuitive justification for why this theorem holds, and in particular for why the binomial coefficient, that is, the number of R combinations, appears inside this expansion. But for now, let's consider a few corollaries of this theorem, that is, a few theorems that immediately follow from the binomial theorem. So the first corollary states that the sum for j equals 1 to n of n choose j is equal to 2 power n. Please pause the video and make sure you figure out how this corollary directly follows from the binomial theorem. So of course the hint here for the proof was to use the binomial theorem. So we have a sum here which looks somewhat similar to this side of the equality, and then we have a number to the power n which looks similar to this side of the equality. So to make this work, we need to have x plus y. Remember, x and y are variables, so you can replace them by anything. We need x plus y to be equal to 2, and we would like the x and y here to disappear because we want to have a sum of binomial coefficients, just like here. So by disappear, of course, we mean that this should be equal to 1 and this should be equal to 1. And the easiest way to make that happen is to take x equal 1 and y equal 1. And of course, 1 plus 1 is equal to 2, so we would get 2 to the power n right away. So I'll let you check that if x and y are both equal to 1, then the expression you get on the right-hand side is this one. And therefore, we have just proved this corollary. Now that you have practiced with this kind of proofs, let's look at a second one. The sum for j is equal to 0 all the way up to n of n choose j times minus 1 power j is equal to 0. Again, I'd like you to apply the binomial theorem to prove this corollary. So hopefully you realize that we can complete this proof by choosing x equal to 1 and y equal to minus 1. Because 1 plus minus 1 is 0, so we get this side of the equality. And if x is 1, then this power of x is just 1, disappears in the product. And if y is minus 1, then this term becomes minus 1 power j. And that's exactly what we want on the left-hand side of this corollary. Now finally, I want you to practice this one more time to prove this theorem. The sum for j equals 0 to n of n choose j times 2 power j is equal to n to the power n. Sorry, 3 to the power n. So hopefully you'll agree that by using the binomial theorem with x and y equal to 1 and 2 respectively, we are able to quickly infer this theorem. By the way, as a practice problem, I would like you to go ahead and write a different proof for this theorem. In other words, a proof that doesn't use the binomial theorem. And more specifically, I want you to come up with a combinatorial proof for this theorem. And I will be checking your work later on in the lecture. Now, in conclusion, the binomial theorem is very useful because since x and y are variables in this equality, they can be replaced by any terms. And therefore, the binomial theorem allows us to compute many expressions of this form, that is, binomial expressions raised to any power n.